Now let's recap everything by walking through the sequence diagram of the authorization code flow. We have the same key players, the resource owner, the user agent, the client application itself, the authorization server where the client is registered as a confidential client, and the resource server. The resource owner initiates the flow by attempting to log in or by giving permission for the client to access their resources. The client then redirects the resource owner via the user agent to the authorization server's authorized endpoint with a redirect request. Note that here the response type must be set to code, indicating the authorization code flow is being used. The resource owner authenticates with the authorization server and, if applicable, reviews and approves the requested scopes. After successful authentication, the authorization server generates an authorization code and redirects the resource owner back to the client via the user agent, along with the authorization code and the state as query parameters in the URL. The client now needs to exchange the authorization code for an access token. To do this, it sends a POST request to the token endpoint of the authorization server. In this request, the client provides the authorization code, its client ID, and its client secret for the authentication. The redirect URI is also included to ensure it matches the one sent in the initial authorization request. Lastly, the client specifies the grant type equals authorization code, indicating it's using the authorization code to get an access token. The authorization server validates the authorization code and client credentials, client ID, and client secret. If everything is valid, the server responds with an access token and possibly a refresh token depending on the server configuration. A key difference from the implicit flow is that the client sends the authorization code and client secret securely through a POST request, which is encrypted by TLS and receives the tokens securely. In contrast, the implicit flow sends the access token in plain text via the URL. Finally, the client uses the access token to access resources on behalf of the resource owner from the resource server. The resource server validates the access token and, if valid, provides the requested resources to the client, completing the flow. Now let's see how the authorization code flow solves the security challenge of the implicit flow that we covered in the last lesson. Once again, we have the same malicious application, an interceptor that's capable of monitoring and intercepting browser or network traffic. At the same point in the flow, when the authorization server redirects the resource owner back to the client via the user agent, instead of providing the access token directly in the URL as in the implicit flow, it provides an authorization code. Now here the malicious application will intercept it again because it's monitoring the traffic. Then, the malicious application uses the intercepted code and sends a POST request to exchange the code for an access token. The authorization server will then validate the code and client secret equals I don't know. Since the client secret is incorrect, the request will fail and return an unauthorized response, which makes the hacker very sad. On the other hand, the legitimate client sends the correct POST request with the authorization code and its valid client secret. Client secret equals I know it. And there we go, the authorization server successfully verifies the request and grants the client an access token. This additional layer of security, the requirement of the client secret, prevents unauthorized access, solving the major security risk of the implicit flow. Up until now, everything seems perfect, right? But let's see what happens if the client is a public client, like a single page application, which cannot securely handle secrets because it runs entirely in the browser. So the user agent is now a browser and the client is a single page application. Let's explore the following scenario. As we learned in the client types lesson, a single page application loads everything in the browser, including the entire application code. This means that variables, entries, and any sensitive information defined within the application could potentially be exposed if not handled correctly. The malicious application takes advantage of this vulnerability by using certain tools to obtain the client secret. Client secret, I know it. At the same point in the flow, when the authorization server redirects the resource owner back to the client via the browser, the hacker intercepts again the authorization code. Since they already have the correct client secret, I know it, they send both the code and the secret to the authorization server. And there we go, the verification succeeds and the hacker is granted an access token, leaving the resource owner very sad. Single-page applications, also known as browser-based applications, run entirely in the browser after loading the JavaScript and HTML source code from a web page. Since the entire source is available to the browser, they cannot maintain the confidentiality of the client secret, so a secret is not used for these applications. So the implicit flow is insecure and deprecated, and the authorization code flow is suitable only for confidential clients. So how can we secure public clients? In the next lesson, we'll explore how the PKCE flow proof key for code exchange addresses this exact security challenge by extending the authorization code flow.